Alright, welcome back to Meteorology 101. In this video, I'm going to talk about cyclogenesis, Petterssen's rule, and do a little bit of chart analysis. So if you haven't, visit my website, meteorology101.com, and get your head in the clouds. So cyclogenesis. The easy way to remember cyclogenesis is the first book of the Bible is Genesis, the beginning. In the beginning, so look at the beginning of a cyclone. So the development of a cyclone. Cyclogenesis is the beginning of a cyclone as it starts to develop from either nothing or becomes more intense. So Pettersen's rule, we'll cover that in just a second. And then the chart analysis is going to be for today, March 27th, 2021. So Pettersen's rule. Cyclogenesis can occur when and where an area of upper level divergence, indicated by PVA, becomes superimposed over a low level frontal zone which exhibits weak thermal advection. So, what does that mean? Cyclogenesis, the beginning of a cyclone, can occur when and where an area of upper level divergence, so the winds are going vertically up and then separating in the upper levels. That's divergence. Once that indicated by PVA is positive vorticity advection. So you can pull up the 500 millibar chart with positive vorticity. It shows the positive and negative vorticity over the area. If you have positive vorticity, which is the indication of rotation in the upper levels, that shows upper level divergence. That's an indicator. And that becomes superimposed over a low level frontal zone, which exhibits weak thermal advection. That frontal zone would almost have to be a stationary front or a very weak cold front or warm front. So as a warm front stalls, the thermal advection around that warm front becomes very weak. So if you develop an area of upper level divergence above that, say an upper level low, an upper level major shortwave trough, or anything that's going to cause upward vertical motion over that frontal zone, then you can actually get another low pressure system or a cyclone that can develop over that front. So that's what Pettersen's rule is talking about. So we'll actually show you a little bit more here. Let's get into the charts. First, I want to look at satellite. Let's just go through the satellite real quick. So, if we look at the satellite, we have. Let me get out of there. And look at these. Any features that are popping up. Looks like some sort of frontal boundary. There's got to be a frontal boundary there. Some flow pushing against that front, causing that lift. So, we look for any rotation. The rotation off the northeast coast. Looks like low pressure. That's a pretty wound up system. Occluded low, cold front coming down. I would say that is a frontal boundary. And then any flow offshore that's pushing onto that front and causing that lift over, just over the Atlantic. So if you look at the big picture, look at these lower levels. The semi-permanent high pressure system over the Atlantic, rotating clockwise around a high pressure system, pushing all this moisture in and then into the Gulf of Mexico and then on shore. So you've got some low level stuff underneath this, higher level or mid level to high level clouds, some cirrus spillover, maybe a ridge right there, indicator of high pressure where that clearing is, and then the cirrus over just spilling over that ridge. So it looks like high pressure. Another boundary, possibly this boundary coming in, becoming either stationary or just kind of stalling out right through the southeast United States off of the east coast of Texas. So looking at the flow, possibly a jet stream, ridge. You got the clearing there, so you got the ridge, the jet stream pushing up and then coming up around that low pressure system. So if you look at along the mountains, we got a little bit of intensity popping up right there. So that shows me some orographic lift in the lower levels. If you look at the little bit of convection there, maybe. And then onshore flow, like I said, with that frontal boundary, what to see what's going on. I don't see any rotation, but with this satellite, it's all upper level and low level. So try to decipher that low level stuff at the underneath this, the brighter high level clouds. A little tough to do on this. We can pull up water vapor and stuff like that to get mid levels, low levels, and then see what's really going on. But basically, I just use the satellite to get a overview of what's actually happening, and then we can go look at the surface chart. So on the surface, I got the station plots plotted, and if we want to look at this, we can just look at the ceilings. The blue will be marginal VFR, and then the red is IFR conditions. So you have snow. So visibility is between 1 mile and 3 miles with the IFR conditions, and the marginal VFR conditions, you're looking at visibility 3 to 5 miles, and or ceilings 1,000 to 3,000 feet. So the red, you got the ceilings and or visibility. The visibility is 1 to 3 miles, or the ceilings below 1,000 feet. So you can kind of get an idea of what's going on with frontal boundaries. Get the stable, you get a stable environment, or you got precipitation. You have something stopping that, that's restricting that visibility. So onshore flow, you got some low ceilings or visibility here. We can look at our ceiling is 700 feet. That's why that one's red. So this one's 2,000 feet. So we're between 1 and 3,000 feet. So we're marginal VFR. So that's why those are blue. Okay, so look at the wind directions. Look at the pressures. The pressure on these station plots on the upper right hand corner, like this is 1,011.3 millibars. There's 1,012.6. So basically, you're just adding a 10 in front of this, and then it is a point. It goes to the tenths of the pressure. So you're 1,011.3, 1,011.4. So getting into a little bit higher pressure there. Nothing significant, but 1,010.4. So, and then look at your wind flows. If you see wind shifts like this, winds are out of the northwest and then out of the southwest. Now you got some sort of boundary there, or you got rotation. So I'm looking at, definitely some troughing right there. Now this wind coming from the west, that kind of stops you with the rotation a little bit. I like to look for the easterly flow. Once I see a wind that's easterly going around the system like that, now you definitely got circulation. Then you can place your low. So the pressure, the isobars, lines of equal pressure. So if we plot these out, basically they're every four millibars, and they're going to be even numbers. So say 1,000 millibars, so 1,020, so 1,024, 1,016. I mean, what we're going to start looking for is there's 1,019. So if we go to 1,020, then there's 1,020.7. Looks like 1,020.7 there. 1,021.3. So now we're getting into a little bit higher pressure. So the 1,020 millibar is going to be one of our lines. So I can use the computer to generate those isobars, and then we can generate the isotherms. So, but let's just take our time with this thing and see what we got going on here. So if we see rotation here, I don't see the easterly flow. I see convergence there, at least confluence. You got the winds coming out of the northwest and then out of the southwest, so they're coming together right in that area. And that's pretty much where we have our clearing. Any of these empty station plots, and then we get broken as we get up to the north. So when we were looking at that satellite, we had a pretty good area of clearing through there. So winds, when you get the winds facing each other like this, you got convergence. Now you could pretty much say there's a boundary there. What we've seen on the satellite was a low pressure off the coast. Then we were saying that front coming around and then coming back into the United States and then pushing in. We could say where our winds are, where we have convergence like this, we could say possibly a frontal boundary right there. So it looks like a little bit more rotation right here. We do get the winds to kind of come together right there. So if we had to maybe place a low right there, and then that frontal boundary coming out of that low, and then we'd have a wind shift, winds out of the west, winds out of the southwest. So you got a wind shift to maybe have a little bit of thermal advection there. But you want to look at like 79 degrees, 78 degrees. So that's not a real big temperature drop. Your main temperature drops back here 78 to 65. So I would say that there may be a cold front right there, 63 to 66 to 81. So maybe bring a cold front down out of that. And so I would probably say there's a pretty good chance there's a low pressure system right there over Texas. If there's not, then there could be one developing. Like we said, Petterssen's rule, we have to look at if there was a stationary front coming through the southwest United States and then an area of upper level divergence indicated by positive vorticity, then we could definitely place our, say that there could be a low pressure system forming up right there. So high pressure, we've seen the high pressure on the satellite bringing all that moisture, those clouds over the ocean up into the Gulf, and then that's what there we got our southerly flow, onshore flow, and then any friction mixing that happens along the coast, you're going to get all the moisture being pushed on shore. And then if there is a frontal boundary there, it hits that frontal boundary, there's your lift to cause lower ceilings and precipitation. So see what we can pick any of this stuff out here. 2015. Let me get to my drawing here. Let me see if we can start a drawing. Try to pick out some of these isobars ourselves. The computer, what the computer's going to do is, we throw the isobars on here. It's going to analyze this chart, but it's going to smooth all the isobars so they're nice and neat looking. So if you actually analyze a chart, and this one's pretty crowded now, but we can even crowd it even more, but it gets hard to read. But you go to station, you break down state to state, you can actually plot those lines, and they'll zigzag quite a bit around those stations where the actual pressure is, because it's real hard to get a perfect read on that pressure. Because it's so, if the charts analyzed it the way it's supposed to be, it would just look like somebody just took spaghetti and threw it all over the chart. So the computer has been programmed to smooth all that out to give us a better understanding of what we're looking at for lows and high pressure systems. It's just to give you an idea what to separate the lows from the highs and see what systems are pushing through. But if you go down into the detail, then you can find where you're going to have a little bit more intense weather, where you're not. So 76 to 56, I mean, we got a wind shift right there. 73 to 56, I mean, I'd say possibly even a frontal boundary right through here. 72 to 75, there is that wind shift, but that temperature difference doesn't make a big difference. You got a 60 on the dew point, 50 on the dew point, so it is a little bit drier behind that. You do see the moisture there, so it's drier behind the front. But we could, like we said, there's a big dry area through here anyway. So let me get to, see if we can put some isobars on there. That's just through the fronts on there for me. I didn't want to do that. Actually, let me go get rid of this. See if it's going to let me get rid of this. I'll just erase it all. Throw my plots back on here. Give me just a second. Alright. Let me start a new overlay so we don't get confused on what we want to do. Okay. Alright, 1015. So we're pretty close there to 1016. If we find the 1016 millibar area, maybe start plotting a little bit. 1013, 15.6. Let's see. 14.5, 1011.3. I see a little rotation right there. 1021, so 1021.9, 1020.6, 1015. So 1020.3. Now we got our 1020. We can try to bring that around here. There's 1017. That's going to be lower pressure. 1021. This was 1020.6. So we can bring this around on that side of that station. 1021 is a higher pressure, so we need to come back over this way. There's 1019.3. So break that down. 19.8. Now we're getting into a little bit lower pressure. We need to come back around that one. There's 1020.2. So you can see how these things zigzag through these, around these stations, so you get more of an accurate idea. Now, if this was, depending on which side the higher and low pressure is on, so we say 1021 over here, 1019 over here, we got lower pressure on this side, then we have ridging right there, troughing right there, ridging right there. So now we can just break it down. You have a short wave, you'll probably have a little bit more. If you have troughing right here over South Dakota, then you could have an area with a little bit more intense precipitation, or you'll get precipitation in that area, but you won't to the south. So we got the cloud cover. We are overcast right in that area. We're broken or scattered to the south, where we have that ridging into Nebraska. So you can see just those minor short waves coming through, and that would be, just little areas of more cloudiness, more moisture if the dew points are there for us, and if the moisture there, instability lift, you got a trough coming through, give you your lift, you can have that precipitation. So, all right, let's continue. 19.8, 20.2. There's 1017, 1021.6. So I'm gonna stay on this side of that station. 1018 and 1021. So we're just gonna come on down around here. 1018, 1013, 11. So 1018, 26. We're staying. Now we're coming back over this way. And then we got 1020.6, 1019, 1017. So we're going back, just kind of wrap back around on this 1015. So we're just going to bring this on down here. All right. There's one line. That's our 1020. Let me see what I got to do. Do a new segment and start on this side. Let's start trying to find. We got 1020. Let's go into the lower pressure. We're going to be looking for 1016. So 1011, 1013, 17. I mean, 16 is going to be tight right through there. That's actually going to be on this side of that one. There's 1016.3. It's even going to be over here. 1017, 1015. So look at our wind flow. Keep an eye on your wind flow. Kind of as these isobars go around these stations, they do kind of stay with your wind flow. They're not always perfectly parallel because you do have friction. The winds will slow and back with that surface friction, so you can. They're always not going to be perfect. So let's see what else. 2011. So that's lower pressure. We get out to 2014. So 2011, 15. So that's 2015 there. There's 1011 right there. So we're going to 2012 would be one. So 1011.6, 2013, 2013, 15. So we got higher pressure in the center there, lower out. Let's see. 15 is going to stay out of that low. 1018. So we want to find the 1016 is actually going to be, that's 1019. So I might be able to bring this thing around. We got 1020 to 1016. Let's go put 18 out there, 15 in the center. So if we get 1016, we could almost bring that I almost want to close something right here, but I don't see, we do have this rotation. $1,011.3, 1012, almost bring out 1012 right around here. What's this one? 1000, I can read that one. There's nothing on that one. No station pressure. This one's 1013. So let's go right around here. Let's go. There's your 1012 right there. So we're pushing through that station. 1011.5, 1010. $1,012. Getting into lower pressure, then we just shoot up to 1015. 1011 to 1015. So 1012 is going to shoot around. I'm just going to just shoot over this way with that thing. Let's see, 15. Yep, right there. Right there. There's 16, 14. To 12, there's 11. It's going to come back around this way. 13. Stay on that side. 1011, 1013, coming right down through here. 1012 and a half, 12.5, 1000, can't hardly read that one right there, 17. Then there's nothing there. That sucks. I need that one. 1009. I'm going to bring this one down in through here. There's 1014. Okay, 1010. Okay. I'm going to just bring this one right here. Start a new segment. Bring this one up. And we don't have that station. We got 1013 there, 1013 there. We can go up to this way. Let's go. And then that's 1014. Okay, bring that one up there. Okay. Now, if we want to center a low, we're looking for rotation with the winds. And then we're looking for a little bit lower pressure than our 1020. We need 1016. Then 1012. So we hit our 1012. Went lower pressure here. That was 1020. We still need a 16 or something, but we're still lower there. So we said 1012. We're 8 millibars difference. We can plot every 4. So basically, we're looking for 1016 millibar center low, or less. So there's 1012.6. 1010, 1011, 1009, 1009.8, 1009.9, 1009.4. So right down here is where our low pressure system is going to be. So we're going to have to just place our low. Let's see, where are we going to go with it? 1012, 1009. 0.9, 1009.8. We're lower pressure over here. 1009.7. We're even lower over here. But we don't have that easterly flow either, so if we went around this station, we could almost go with 1008 millibar low right there. Okay, let's throw a low right there. Okay, now if we had a stationary front coming through, we did have those winds that were kind of facing each other right through here, so we could almost have 78, 80 degrees, 80 degrees, so we could throw an isotherm right across there. 82, and then 80, so our isotherm's coming right around here. We do have some thermal advection right there, 75 to 80, so southerly flow, so a little bit of warm air advection right there. Let's go and throw our isotherms on. Now, I'll do Fahrenheit for now, but they can get pretty crowded too, so we may take those off, just go Celsius. See how crowded this is. See, there's way too much going on. It's every 2 degrees Fahrenheit. Just makes it look a lot worse than it is. So remember, take that one off. Let's go Celsius. So if you want to convert to Celsius, just times 1.8, add 32, and that'll be Fahrenheit. So we know we're in the 80s over here. We got the surface plots to see about where we're at anyway. So now, where we're talking about cyclogenesis will occur when and where an area of upper level divergence becomes superimposed over a low level frontal zone, which exhibits a weak thermal advection. Okay, let's go after this. If we were to say this is a low pressure center, got a little bit of a wind shift here, but let's go warm front, and that's, if there's any thermal advection there, that is weak thermal advection. Now, this wind shifts here kind of all over the place. We do have the mountain range there though, so we will have quite a bit going on for wind differences. You know, you can get winds coming off the mountains, you know, being an easterly flow, and then over Tennessee right there you see the westerly flow. So if we set our stationary front, bring that out of that low pressure system into our right there into the warm front that exhibits a weak thermal advection, and we'll go cold front. I mean, you're still talking weak thermal advection. You know, temperature difference is 90 degrees to 66 degrees, so there's definitely a cold front there. So let's pull that out of, come on, right there. Okay, so need a way to label these things, but we got see 1012. We have to go into higher pressure on the, we know that higher pressure was off the east coast. We had lower pressure to the north. So where our higher pressure isobars are, we got 1070, now 1023.5 would be 1024, 1024.8. So 1024 would be one, 1020 would be the next one. So we're at 1012, 1016. We're looking at a 16 right here. 16, 15, 17.3, see, 15.2, 17.5. So if we're looking at our 16, we're going to go from 1015.1. Okay, 1017. So we're just going to bring this right on down through here. And there's 1015 there, 1017 there. Bring that through. 1016, we're going to hit that station. And then That one doesn't have one. 1016.9, so a little higher pressure on that side. So we want to stay over here on this side of that station. And I covered that one up with a warm front, so 1020.7. Still going to come right around here. That one's not listing one. 1019. So we want to stay over here. 1020. And just bring that one on down. Okay. 1016, now 1020, because we're going into higher pressure. Then we're going to go back into lower pressure, so we got to be careful. There's 1020 up there. 1018. So now we're getting to higher pressure, even up into that area. But we knew there's low pressure up to the northeast off the coast. But we're going to have high pressure behind that. So because this cold front, basically a cold front coming into a stationary front. Look at these isotherms. We could pretty much say if you had, there's some thermal troughing there. Just depends on where the trough is coming out of that low pressure system. You know, if you're going to have a baroclinic system, that thing is pretty wrapped up. It's almost becoming barotropic, so your isobars are not going to be too perpendicular to these. They're going to cross them, but they're not going to cross them a lot. So we got 1019 over there. There's 1020 right there. 24. Now we're getting in the high pressure center. 1019. So we can see if we look at the wind direction here, then coming back from the east to the south there, then you could pretty much place your high pressure system somewhere out in here. With 1024 millibar, 1024.8, that's even higher. So if you wanted to, you could almost go high pressure right there. Let's just go ahead and throw one in there. We know that's to the south because all that high pressure was pushing that flow goes this way. So clockwise around that high, we're pushing all that onshore flow. Our winds are coming from the south, so we know we have that onshore flow. So we're at 1016 here. Let's get back over here. Let's go to 1021. Actually, I can drop that down too, and where our isobars are here. 1019, 19, 18, 19, 22, 23, 20.7. Let's go down here a little bit more. 20.7, 18, 21. Okay. So we were to put our high, we're going right through those winds. 1018, 1019, back up through here. Okay, 1021, we're going to stay to the south of that, north of the 19s. 1021, that goes around there. 1023, 1020, 0.5, 0.7. So that's all going to stay on the outer edge of that. 20.3, we're even coming over here. Wrap it around that station. 1020.7. And then that one's a little hard to read. 1015.6 it looks like. So this was 1016. We crossed into that. So there's a 1020.3. What's this one? That's not giving us anything. 1017, 1013, 1014, 17. So let's go back up. We ran into our 1016 there. So that one is going to come back. That 16 needs to come back over this way. This 20 is going to come back over this way. 1020.7, 20.5. That's 1019.4, 1024. So that's 21. 1020.6. 1019, so we're staying on over here. 1021, we'll keep the high pressure on this side. 1020.7, 1019.1. See, these things will zigzag through these stations like that. What's that one? 21.9, 22.9, 20.7. So now we're getting into lower pressure up here. So this is going to have to end up. We're going to have to end this one, bring this one back around. Can't get over that far. Be 1,003. That's a real low pressure. So now we do have a low pressure. So this is just going to drop back down over here. That's what this one's going to do. We're going to go. See if we can undo these things. Back up a little bit. Now if we want to bring this back below that, and then we got 1,020 something there. I don't know what that is, but we can pull that over there. We'll just leave it that. Leave it with that one. Okay. So high pressure. Then we're going to go into low. So we got our 1,020. We'll go back into a 16. We were 16 over here. We crossed a little bit. We need to bring that one needs to come over, but I can't fix that right now. We'll go 20 to 24. We don't have. We got a 24 up here. That's a higher pressure. So 1,016 basically. Man, this is going to be low. Let's go back up. If we can get up in that area, that's going to be the tough part. So 1,011, 13. 13.9, 16, 23. So we're definitely getting high pressure there, low pressure there. Some just smaller areas. So this cold front, that's actually going to be stationary. That stationary front's probably going to come right even back through here. And then our cold front, once we get into any thermal advection, if we draw out those isotherms up here, there's 1,000. Actually, that's a 996 right there. Okay, low pressure right there. We'll put low pressure. Grab my low. Let's go with this rotation. Just with the sparse data over the ocean, it's hard to say. We got 1,096. I mean, if we wanted to throw some rotation, we definitely got rotation there. So we throw our low right in this area. Okay, now as strong as that low was on that satellite pic, let me get over there with you. So right here, it's a pretty, looks like a pretty intense low. Maybe a post frontal trough or a post front, but then that front coming through right through the United States here. So look like a pretty intense low right there. So we know we got low there. Clearing to the north. Can't really see anything there. Clearing, that'd be kind of like a high right there behind that front. So right off the coast. High pressure we said down to the south, pushing all this to the north. Jet stream flowing through, ridging on the jet. Look like maybe a deep trough over the southwest, and then coming back up with the jet stream and then ridging. It almost seems like if you look at the cross flow here, like south pushing to the south and then pushing to the north. I mean, that would be an indication of maybe a cutoff low forming right there. You see that rotation? You can almost see it pushing south, pushing north, to like a jet stream's coming down, cutting too tight, pushing up, and then just cutting. If it's going to just cut off or leave a low pressure system over there, maybe. Sometimes they'll actually fill, that low pressure will fill, and then you'll never get that low, just sits there. But a lot of times if the jet can't make that turn, it just overshoot and then leave that low pressure sitting there spinning, and they'll sit there around the Four Corners area just spin until it fills and then just dies out, causing precipitation, clouds, everything over the Four Corners. And then unless you get like a major short wave that comes from the west, and then that's a kicker, it hits that low pressure system and it kicks it off and then becomes a well-developed low over Texas and then pushes to the northeast along with that flow. So that's something to keep an eye on there. Alright, so low pressure system up here, high pressure system. I'd say a little bit of a high there, low there, high there, and then low down in here somewhere. We got all this advection going on, so we got that jet pushing the cirrus over that ridge. So we know we got a ridge right there, and then with this lift, we got that frontal boundary. Just looks like it's coming right through there. So let's get back over to the charts. Alright, we got that frontal boundary, low pressure system. It's a high pressure system. We got that ridging, definitely got that ridging there right behind that low. So we could almost just bring our cold front right out of that low. I'd say it's probably going to be an occluded low anyway. So you're going to have an occlusion, but we're up in the corner of the chart, so it really doesn't matter. So we could throw maybe this cold air, and with our southwesterly flow right there, we can throw, that's a pretty strong 30 knots, but it is over the water, so there's light friction over the water, so you will get higher speeds in the wind flow. But if we just bring our cold front down, then we can say possibly going to have isobars around this ridging, a little bit of high pressure here behind that front, and then that front just connecting into the stationary front. So let's go ahead and do that. We're not going to go occluded right now. We're just going to throw our cold front. We're going to keep that southwesterly flow in front of that front, and then bring it down into here, and then we can just connect them too. Alright, now my program doesn't crash on me. Sometimes it does. There it did too. That's got an error that popped up, so I'm not going to be able to draw anymore on these charts. That kind of sucks. So what I'll do here, see if I can do something else. Use a different drawing program. Let me throw my display up here. We can do here? What's our display there? What do we got? Okay, we're pulled over. Okay, so we got the display here. Let's see. Stretch this out a little bit. Okay, now let me go here. We can do, I don't know if I can do a black or not though. If I hit B, I think there's a black board up there. We can use red or blue or green maybe. Okay. Alright, having trouble seeing that one. Okay, there it is. I don't know if you guys can see it. Okay, it's on there. So once we get some lines, we'll get going. 1000, what do we say? 1020. So we're looking for 1000. There's 1022. See any rotation for a high up in this area? We got winds out of the north. So we've got that 1020. That was 1020 right there. 1016 maybe. That's 1009 right there. We do go pretty low. That'd be 1012. That's what we're really looking for. But we have a 1016.1 right there, so it looks like it is going to be a 16. Then there's a 13. And that one doesn't have anything. So we drew something right through here. Then we're going to cover up our numbers, so it's going to be hard to read. That was an 18. So we basically went after 16 here. So that's going to come down and then probably just go back around this way because we got the 1020 right there. So we're probably just going to kind of follow that along. And then we can go. We Well, you're not even on the chart. You can't really see that thing, so that ain't doing us any good. All right. Let's get back over to. Let's go to back over the United States. There's a low pressure system there. There's you can see now the isobars. If you see that green, that's starting to cross over those isotherms. So we're going to bring this back over. We have that low pressure to the south. Stationary front. Look for 1014, 15, 14, 1011. So it's going to be 1012 right up in here somewhere. So we're 12, 20. We have a 16. We have 16 in there somewhere, and then there's going to be another 12. There's a westerly or easterly flow right there, but then we're coming northwesterly, so we just got a boundary right there, it looks like. And then we'll get that wind shift right there, say 1018. What's that? 1015.5. You almost have a low right there. You know, we encountered an error, so we can't even put a low there. Alright, we're just erroring out now, so alright, I guess that's about it for the drawing. I don't think I can do anything else. I can just go manually draw, but they don't stay. You know, you can see the low, but that don't stay there. Alright, low pressure there. Back to what we were talking about, Petterssen's rule. Let's go pull up a vorticity chart. Alright, we're going to lose all this. Low pressure to the south. Weak thermal advection. We're looking for vorticity over Oklahoma, Kansas, Nebraska, Missouri, Arkansas, Iowa. Let's look for any advection or any vorticity advection in that area, especially to the south over this frontal system, to see if this low pressure system is going to continue to develop. We'll go look and see where our jet stream is. Does this low pressure, how far up in the upper levels is it going? It's pretty weak, so it's probably not going. There's probably a trough in the upper levels, maybe. With any vorticity advection, then we would look for that low to intensify, or along the stationary front, if there's any vorticity advection, to start getting any kind of rotation to start a new low along that front, and this one just fill out. If there's one to the north, you know, just an elongated low or just a low pressure up there, like we said, then these two low pressure systems being stationary with this weak thermal advection, we could have a low, those two come together with the vorticity, wherever that vorticity is, and then bring that low pressure system together and start developing pretty good on that. So let's go to the 500 millibar chart. Let me get you back over here where you can get a better view. And let me get back here. Run vorticity. That's going to erase that. Start over. Okay. All right, so we do have it over Arkansas, Oklahoma. Let me go throw the vorticity lines on here so you can see where that advection is. So, I mean, if we have any advection, that's kind of weak. Well, it does have that positive advection into the negative, so we are pretty accurate right there. Like I said, let's go ahead and we'll just put let the computer put the isobars on here. Put our lows and highs. Let's see what it generates. Okay, it did have a low pressure system to the north, just that low. They had that well to the south, way further south than what I had it. I had it over Texas. So they had 1,007 millibar center. So we got that troughing out of the low pressure system over Mexico, pushing in, and then I don't think it's going to allow us to do fronts. We don't air it out on that. There's the high pressure system, 1,024 millibar center over the Atlantic. These isobars got pretty tight. That's a 500 millibar. Anyway, that doesn't matter. That's the 500 millibar heights. But you can see the thickness lines. We could probably say our jet stream. Where do we have that? Let's go back. We'll go to the 300. Look at our jet. We'll pull a thickness chart too, and that's going to give us an idea of where our jet stream is. But right now, vorticity over North Carolina, and if that stationary front comes down through North Carolina, we could get a low pressure system pop up over that too. Excuse me. So we need to look at this low pressure system, weak thermal advection, and low pressure well to the south. This becoming one system and just actually creating a low right there. That we know there's going to be a frontal boundary come through. Troughing, we are expecting some weather to come through Tennessee, Kentucky. All this is going to push to the north, but either that low pressure system is going to become more well developed, or the combination of these lows become more of a well developed system when if they merge together and then push off to the northeast and then cause pretty significant weather. We need to watch and see what kind of if there's any severe weather in Tennessee and Kentucky. So we'll pull up some models too to see what the models are picking up for this. But we do have that significant positive vorticity over that frontal zone. So cyclogenesis can occur when an area of upper level divergence becomes superimposed over low level frontal zone, which exhibits weak thermal advection. Right there, weak thermal advection, upper level divergence indicated by PVA. Right there's your cyclogenesis. That low pressure system or this low, they're going to converge, or we're going to get a low pressure system develop right over that. All right, get a drink. Okay, I need to restart the program to do the fronts, to let the computer place the fronts, but it doesn't do a very good job of that anyway, so I'm really not worried about it. I'd say stationary front. High pressure. You got the ridging. Let's go back to the surface. Let's go see what we got here. All right, high pressure. We got low pressure, ridging, troughing, ridging. There's your onshore flow from the high pressure system. Onshore flow, the southerly ones we've seen. That weak thermal advection. Let's throw our isotherms on there. And then get the surface plots back where we were, and then we can see, let's look at some temperatures of dew points, see where we're at. That's some pretty strong, those isotherms are pretty close together, but being parallel with the isobars, there's really no advection, so we don't have to worry about it. But if you look at some dew points here, see a 20, 64, that's pretty dry. There's your dry line right there. 80 and 20, that's dry. 82 and 64, that's a little bit significantly more moist, with 78 and 52. So if we had to place a dry line, to place it right through here. 68 and 30 possibly. So right there over out of the panhandle of Texas, that's where you're going to place that dry line. Any of this warm, moist air, that positive vorticity, that's a little bit further east, but that dry line being another, acts as almost as a frontal system that pushes through, and that gives you your lift, and we could get some significant weather over central Texas. All right, now let's go look at a jet. I want to see what a jet stream is. Let's go real quick before we get off the surface. Let's just look at the thickness chart real quick. It'll take a second to build this thing. There's a lot of data on there, so it just, for some reason, it's a little slow building this chart. All right, there's a 500 millibar thickness. There's a 540 line. That's our rain snow line. Anything to the north of that should be snow. Anything to the south should be rain. So we don't have to worry about any snow. What do they do up north? Minnesota. Wisconsin. Okay, so our thickness lines, if we look at those, see that tighter packing through these thickness lines, that is a ridge right there. That's where we were saying there was a ridge. The cirrus blow off spilling over that ridge. So we would have to put, we could put the jet stream right there through the tightest packing. So let's see. If we go put the 300 millibore jet on here, I don't know if that'll probably just cover up everything if I do it right now. I can do an overlay, but it'll just blank everything out here. So, all right, let's guess our jet stream. I'm interested in seeing you can see that rotation right there, but I'm interested in seeing if we go to the upper levels, see the jet stream wrap around and see if we're going to get a cutoff low. That's one significant feature we're going to look for there. And then we know we got our ridge there, and then we got our troughing, and then that jet shooting back up over that low pressure system up to the northeast. So that's a pretty good indicator for your jet stream. And then you have north-south temperature gradient, how tight that packing is, and then the 500 millibar thickness heights. That's going to give you an indication of snow, rain and snow. So let's go up to, say, 250 millibars. And let's do some jet stream shading on this and see what we got here. So we do have a different jet finger there. We got jet stream coming down. Looks like it is going to either be steering around and then back up to this finger, and then we got the ridging, and then the trough over there. Then that's actually a little bit further south. So if that front was there, that low pressure system up to the northeast is dying out pretty good, and it is more or less a stationary front just shooting right through there to get this jet stream over that. So, because if you had a well-developed system, your temperature gradient that's what causes north-south temperature gradient is what causes the jet stream. So you get that low pressure system. If it was way more intense, then you'd get the jet stream shooting up back around that front, or on the back side of that front over the north side of that low. It's going to pull up some pressure at the 300. Then we throw the isotherms on here. We can throw station plots for radiosonde data. There's pretty tight thickness right there. We can throw streamlines and show us our flow, but we can pretty much see that. Actually, let's do that for the purpose of this system to the southwest. I'm going to see what's happening there for our flow. First, I'm going to throw the station plots on here just to see what the balloons picked up. This is real data, so. Alright, so 130 knots, 100 knots, 130, 140 knots right there. And get some streamlines. Okay, so not as significant as I would think on that. For the flow, not real deep of a trough, but we do gotta have. There's a little more westerly than I would think. Now here's where we're getting to the northwesterly. I'm trying to make up a cutoff low. I don't think it's happening. So if anything, that trough's going to fill, and then our jet stream just going to kind of become more streamlined across the United States. There, we got the ridging, and then that goes back into. Well, we have two fingers here really going on. We could have this coming down. I mean, it's cutting over here pretty good. I'm not so sure I'm not right on that one because we got that 45 knot wind right there to a 45 knot wind, and that's almost northeasterly, and then wrapping back around. So we could definitely have that cutoff low happen. Let's go look at some models real quick, and then let's see what they're going to tell us. if we pick up any low pressure system over the southwest, and what kind of convection we're going to get over Tennessee, Kentucky area. Get to okay. Didn't want to really do that. Just picked up a sounding. Get you guys in the screen here. It's pivotal weather. You're clicking on an area, you can get a sounding. You see what your moisture content's going to be. All right, so there's a low pressure that popped up over Illinois. So we already had a low pressure system in that area. Still, if you look at the little closed low right there, that's a really elongated area of low pressure. Let's go all the way back. Okay, we're all the way back now. See how these things are initiating for a model. So 1010, 1012, 1010. So 1008 there, it does have that center down in Texas. Like I said, when we analyzed the charts, we had I had a little bit further north, but we had just had that big long trough. But if you look at these isobars, how they kind of zigzag through, these models do a pretty good job on exactly where those are going to be. I mean, they're never exact, but because it is a forecast model, so you got to take them with a grain of salt and just use it as a tool. So we got low pressure system pushing north. We got that one right there developed over Illinois, which you already kind of picked that up on the charts too. Now we got our thickness lines. These are the 500 millibar thickness lines. There's our 540 line, going perpendicular to the isobars, the surface isobars. So we got, we do have temperature advection. Now we do got a pretty intense system right there over Tennessee. This is 12Z tomorrow. It'll be like 7 a.m., 8 a.m., 8 a.m. Eastern time. And that looks like that low pressure system developed, went out of Illinois shot straight to the northeast, and a frontal boundary coming through. So I didn't see any low pressure system starting over there. Now we'd have to go up to a higher chart to see if there's a cutoff low, because if there was a cutoff low in the southwest, that would be over the southwest, and that would be in the upper levels. It'd be an upper level low. So all right, so we got that low pressure system over Mexico, low pressure system right now over the Great Lakes region, over Michigan, maybe not quite Michigan, and it's kind of staying right there, pushing to the north. The one over Mexico just kind of goes away. We still got low pressure in that area, but it looks like it's just kind of hanging on the tail end of that front. It looks like it just becomes a big frontal boundary, just pops up out of nowhere. High pressure system out of Colorado, ridging, then that pushing south, and then shooting up to that's just kind of shooting to the east with the high pressure system. So right behind that, ahead of that high, is where your frontal boundary is. So that's just high pressure pushing through, and really nothing significant developing off the tail end of that low. Now the models could be not picking it up either, because we had pretty significant PVA, positive vorticity advection over the Arkansas. So what happens there? We got 6Z. It's like 1 o'clock in the morning. Let's see what we got for. And that shows where the strongest areas of convection is over Arkansas. So positive vorticity, and pushing up into Tennessee and Kentucky. So our positive vorticity is there. So, but still, if you look at that, it's a closed isobar right there. That could be picking up a little bit of a low starting right there, but it's not developing. Significant troughing, strong thermal advection, and then you get into the mountain range, and then all that stuff pushes over. Some of it makes it crossed over into North Carolina. A lot of it rains out over the mountains. That's real typical. See how it just breaks up over the mountains, and then some of it to make it over there to the east coast, and then you got high pressure dominating the southeast. This is on the 29th, 15Z, about 11 o'clock in the morning. So that's on Monday. All right, so that's pretty much it for this video. I'm going to end it here. That went on for a while. Hope you learned something on the analysis. If the computer program didn't crash, we could complete that chart. If you want to see more of that, let me know in the comments. And what we'll do is we can isolate them, analyze those charts ourselves, and then see what we come up with, and then compare it to the computer models. And then it's just fun to do for a hobby. So if you want to see more of it, let me know. If you want to learn more about plotting charts, I have all my information on meteorology101.com. So hit the like button, hit the share button, hit the bell, get notifications on my videos, and thank you for watching.